Hi, my name is Jesper Stensgaard. I'm a staff scientist for mixed signal products at Linear Technology, and I design high-resolution SAR A2Ds. Today I'll talk about our new 20-bit SAR A2D family, the LTC 2378-20. The key feature of our 20-bit A2Ds is their exceptional linearity. They are the most linear A2Ds on the market today, bar none. Beyond amazing linearity, they provide the speed, versatility, and ease of use you expect from SAR A2Ds. It's a powerful combination that enables many exciting applications. First, let's take a quick look at the basic function. The 20-bit A2Ds are pin and software compatible with our 16 and 18-bit A2Ds, all of which are available in tiny packages about 3 by 4 millimeters. When you provide a rising edge on a convert start pin, they sample a differential input voltage and perform a self-timed sequential conversion process, resulting in a 20-bit word that you can read on a serial interface. The maximum conversion rate is 1 million samples per second while consuming only 21 milliwatts from a 2.5 volt power supply. The A2Ds provide numerical values representing the differential analog input voltage relative to a reference voltage. Full scale is set by applying an external 2.5 to 5 volt reference. Now let's talk about A2D linearity. INL characterizes A2D error, excluding offset and gain errors, as a function of the input voltage. It tells you the difference between the code you actually get from the A2D for a given input voltage and the ideal code you would get from a perfectly linear A2D. It is preferable to compare A2D errors on a normalized scale, such as parts per million. For 5 volt reference voltage, full scale is 10 volt peak to peak, and hence half a ppm is 5 microvolts when referred to the input. This figure here shows INL measured for a typical part, reflecting that the A2D error is less than about 5 microvolts for any input voltage in a 10 volt range. Now, a 20-bit A2D can provide 2 to the 20th, or about 1 million distinct codes, implying that the separation from one code to the next is about 1 ppm. So you might ask, how is it even possible for the A2D to evaluate an input signal with a resolution better than 1 ppm, as it is implied by this figure? In order to answer that question, we need to consider A2D noise. The noise is very low indeed, specified as 104 dB SNR for a 10 volt peak-to-peak sinusoidal input. That corresponds to an input-referred noise level of 22 microvolts RMS, or about 2.3 codes RMS at the output. Accordingly, for a constant input voltage, the output from the A2D will span at least several codes, as is shown in this figure here, taken from the datasheet. Now ask yourself, what is the uncertainty associated with a single A2D conversion result? You may decide, for example, that the uncertainty should be characterized as plus or minus 3 standard deviations, which here is about plus or minus 7 ppms. As you can see, a single conversion result does not provide ppm level certainty. The uncertainty, however, can be reduced by averaging. For example, by averaging 50 conversion results, the uncertainty will be improved to about plus or minus 1 ppm. The INL parameter we discussed before can be measured very accurately using averaging. The fuzz you saw on the INL plot is simply a very small amount of noise associated with the measurement. Noise can be reduced to almost any extent by averaging, but the uncertainty error will ultimately be limited by the INL. INL, therefore, is a very important parameter for precision systems. Now let's consider an interesting way to use the A2Ds. Some applications require the ability to evaluate a signal with great precision and also with some bandwidth. More bandwidth means more noise, so you'll need 2 digital data streams. One data stream is low noise, low bandwidth, where accuracy is limited by the INL, and another data stream provides higher bandwidth and has higher noise. The conventional approach is to use separate A to Ds for each of the two data streams, where each A to D is optimized for either accuracy or bandwidth and noise. Our 20-bit A to Ds, however, are optimized for both objectives, and a single A to D may be used for both data streams. Used in conjunction with a digital backend, they can provide state-of-the-art performance at any sampling rate up to 1 megasamples per second. So in conclusion, the 2378-20 is a milestone in A to D history, providing unparalleled linearity and low noise at low power. It is a general-purpose A to D that can be used in place of conventional specialized A to Ds without sacrificing performance. The general-purpose nature of the A to D provides flexibility in your state-of-the-art system design, enabling you to, for example, reduce cost, increase throughput, provide configurability, or to derive some other benefit. I hope these A to Ds will help you to improve your next design. Thank you for watching.